So, when you're dealing with complex numbers, you're often trying to find an angle, something we call the argument. But here's the thing, finding that angle has a surprisingly common trap, one that can lead you to answers that are just flat out wrong. Today, we're going to dig into that trap and, more importantly, find the right way to solve it. Let's get into it. Okay, just imagine for a second you ask me for directions. How am I going to respond? Well, I've basically got two ways to tell you how to get somewhere. And this simple idea is actually the key to understanding complex numbers in a whole new light. And it turns out these two ways of giving directions map perfectly onto complex numbers. The first method, the coordinate one, is the standard form we always see, z equals a plus bi. The a is just how far you go left or right, and b is how far you go up or down. But that second method, distance and direction, is just as good. For complex numbers, that distance is what we call the modulus, and the direction, well, that's the angle, the argument.
All right, so let's make this whole direction and angle thing a little more official. To do that, we need a map. And in the world of complex numbers, our map is the complex plane.
Okay, so here's the textbook definition. The argument, which we write as argz, is the angle, usually called phi, that starts from the positive horizontal real axes and sweeps counterclockwise until it's pointing right at our complex number. It's literally just the direction part of our distance and direction method. And this map, it has a name, the Argand diagram. It works exactly like a regular old coordinate plane. The x-axis is for the real part, and the y-axis is for the imaginary part. So a number like z equals 3 plus 4i is just the point over at 3, 4. Simple enough, right?
Well, this is where we hit our first kind of weird complication. You'd think that for any single point on our map, there'd be just one angle to get to it. But that's not exactly true.
I know, that sounds totally bizarre, but it's a really crucial idea to get your head around. A single complex number doesn't have one argument. It has an infinite number of them. How on earth is that possible?
Think about it like this. You're pointing in some direction, let's call the angle phi. Now what happens if you spin around a full 360 degrees, or 2 pi radians? You end up pointing in the exact same direction. The point on the map hasn't moved an inch, but your angle is now phi plus 2 pi. And you can do that again and again, or spin the other way. You always land on the same point, but with a different angle value.
Yeah, having a bajillion answers for one thing isn't super helpful, is it? So, to solve this spinning problem, mathematicians came up with a simple convention. We define something called the principal value, and we write it with a capital A, argz. It's an agreement that we will only use the one angle that falls in a specific range, from negative 180 degrees up to and including positive 180. This gives every number one single, unique argument we can all agree on.
Okay, cool. So we have a standard range. Problem solved. Now we just need to calculate it. And this is where so many people walk right into a very common and very wrong trap.
I absolutely love this quote from a user on MathStack Exchange because it's so blunt. It doesn't say it's sometimes wrong or you have to be careful. It says it's just wrong. That's a pretty bold claim. So let's put it to the test and see what they're talking about. We're going to use the complex number z equals -1 minus I. Now, just by looking at it, the real part is -1 and the imaginary part is -1. So on our map, that means we go left and then we go down. That should put us squarely in that bottom left box, the third quadrant. Keep that in your head. Now look what happens. If we use that simple arctan y over x formula, we get arctan of -1 over -1. Okay, that just simplifies to arctan of 1. And the result of that is pi over 4 radians, or 45 degrees. But wait a minute. 45 degrees is in the first quadrant. Our point is in the third. The formula gives us an answer that's on the complete opposite side of the map. And that is why the formula is just wrong. It literally can't tell the difference between opposite corners of the plane.
So clearly that old way is broken. We need a smarter tool, one that doesn't get confused by a couple of minus signs. And thankfully, computer scientists and mathematicians already built one for us. And that's where our hero comes in, atan2. It might look similar to arctan, but it's a fundamentally different and way more powerful function. And you'll find it in pretty much every programming language out there, because it was made to solve this exact problem.
So what's its secret sauce? How does atan2 work where arctan fails? It's all about information. See, when you calculate y divided by x before finding the angle, you lose crucial info. The number -1 divided by -1 is 1. but so is 1 divided by 1. The formula has no idea which one you started with. But A tan 2 is smarter. It takes y and x as two separate inputs. It looks at their signs first and says, aha, a negative x and a negative y, that's got to be the third quadrant. It keeps the quadrant information safe.
This table just lays it all out, plain and simple. In the first and fourth quadrants, the simple arctan formula actually gets lucky and gives the right answer. But look at quadrants 2 and 3. In the second quadrant, it gives an answer in the fourth. And in the third quadrant, our test case, it gives an answer in the first. It fails 50% of the time. A tan 2, on the other hand, a perfect score. It nails the correct angle in every single quadrant every single time. It is absolutely the right tool for the job.
And this brings us to the big takeaway. This whole problem of finding the correct angle from coordinates, it isn't just some weird niche thing in complex math. Think about it. A character in a video game needing to turn and face an enemy. A robotic arm that needs to point at a specific target. A satellite dish that needs to aim at a signal in the sky. These are all real-world A tan 2 problems. The argument of a complex number is just one perfect example of a much more universal and incredibly useful tool. Thanks for joining us on The Explainer.